Greetings, fellow grade 11s. It's Mr. Thatcher again. Look, I'm back with another stoichiometric calculations. Now, look, so what we are examining today is basically we are looking at a past paper of your November 2017, right? So this is a past paper of November 2017. Let me write it here. This is November 2017, right? Now we are looking at a question that deals with your stoichiometric calculations. Now let's start. The first one, they say 6.1, the decomposition of hydrogen peroxide in the presence of a catalyst at a standard pressure and room temperature is given by an unbalanced reaction. Now they are saying the oxygen gas is collected and the volume is recorded over the period of time. Now the reaction is completed at time t. Now they say now the results are plot on the graph of your volume of O2 versus time as below. Now they say take the molar gas volume as 24.45 at room temperature and standard pressure. Now let's start here. The first question require us to do it. It require us to basically balance the equation. Look, the easiest component of balancing the equation, I usually say, look, start with this one. Look, this is your 6.1.1. You're going to say you are having your H2O2, which is your aqueous solution, which produces your H2O plus your O2. Now, the easiest component for you that you can do in order to balance this is basically you're going to look at, your reactants versus your products. Now, look, now within your reactant, what is it that you have? Now, if you can start here, look, you are having H2 and you're having H2 this side, right? Then now, which means, yes, we can say, they are balanced for now, but you are having also your O2. And this side, you are having only 3 atoms of oxygen, while this side, you're having 2 atoms of oxygen, right? Which means now it is going to bring us, to our thinking in terms of how can we then, balance this. So for us to balance now, we are going to say, look, now if you are having 3 O2, and while this side you are having what you are having only 2, what is it that we can do to try and balance this? Now look, if we can write, let's say we write 2 here. You write your value of your 2 here. Now what are you then going to have? You're going to have 4 hydrogen hydrogen gas, rather atoms, and you are also going to have 4 now O2. So which means now if you come this side, you are only having now 2 H2, and you are going to have 3 oxygen atoms, which means now this is not balanced. But now if you can write your 2 here and see, now if you write your 2, now look, you're having 4 hydrogen gas or hydrogen atoms, and you are also having now 4 hydrogen atoms also this side. Similarly, now if you can check your O2, now it's going to be 4 because it's 2 multiplied by 2, which is going to give you 4. And now look, if you multiply 2 with this one, it's going to be 2. So you're having 2 and 2, which means yes, these equation of ours is going to be balanced now. So then we have balanced it. Now, then let's look at the second one. Now, what is it that we are going to do now? We are looking at 6.1.2. They say, how will the catalyst affect the reaction? Now, I think by now we know in terms of what is the the function of a catalyst. In this case, the catalyst will lower the activation energy of the reaction. So basically what the catalyst will do, the catalyst its least will lower the will basically lower the activation energy, right, of the reaction, activation energy of the reaction, right? So that is going to be the function of the catalyst or the effect of your catalyst. Now then, let's see. Now let's continue. Now we are going to look at 6.1.3. 6.1.3. Let's get some color here. Now they say use the information on the graph. Calculate the mass of your hydrogen peroxide that are decomposed. Now, so what they want us to do is they want us to calculate now the mass of your hydrogen peroxide. So now we are going to start here. If you can come back to this statement, the only thing that you're given, even from this graph, right? If you can check from this graph, you are given a volume of what? Of your O2 gas, right? And you are also given the molar volume, right? We are given the molar volume of also your O2, right? Or rather, they say, this is going to be your O2. Now, what is it that we can do? Now, which means now we can start by working out what is going to be now your moles of your O2, right? And if we are working the moles of your O2, where are we going to start? We know that the only formula that is associated with your STP, it is your N, which is equals to V over your VM, right? That's what we know, right? So now we are going to say, look, if we can start by calculating what is going to be the moles of our O2, because already we are given that from this table, we are given that the volume that our O2 attain, it is what? It is 600, right? It is 600 centimeters. And we know that the 600 centimeters can be divided by 1,000 to get 0.6 decimeter, what? Decimeter cubed, which means here we are going to have 0.6 decimeter cubed over the what we already have your molar gas constant, which is your 24.45, which is the one that you are given, right? And now after that, now what mole are we then going to get? What is the value of your mole? Now your mole of your O2 here, it is going to be given by what? It is going to be given by 0.0245, I think, right? Yes, let's verify our calculator. Yes, that's that. And now, if then this is your mole of your O2, what is it that we can do now from here? So in order for us now to then calculate now the mass of your hydrogen, we are then going to come back and say, look, we were given, or rather we started by getting a balanced reaction for this. And we know that one thing that we can get from the balanced reaction, we can get the number of moles, right? So we are then going to come back and compare the ratio. We are going to say, look, now your ratio of your H2O2, which is your hydrogen peroxide, is to your O2. If we can check this ratio properly, what is it that we know? Now we know that your oxygen, or rather your oxygen gas, is 0.0245, right? That is going to be your oxygen gas. And now, but the ratio first, let's start with the ratio first, before we write this thing. Now, the ratio, we know that this is going to be 1, and this side is going to be 2. And you know that here it's going to be 0.0245, which is your mole of your O2. And now, which means now, according to the ratio, your ratio is 1:2 if you are starting from your O2. So which means now, if you are having 1 mole of your O2 is going to be represented by the 2 molecules of your hydrogen peroxide, which means now here, now what you're going to get here, you're going to multiply by the 2, right, to get to this 2. Or rather, you can simply do what you can simply do here, you can just simply make this your x, and then you cross multiply. So when you cross multiply, what is it that you're going to get? Look, you're going to have 2 into 0.025, I mean 245, is going to be equals to your what? It is going to be equals to your x. So as I said again, you're still multiplying by 2, right? Just in case, you know, you are having difficulties. So this is going to be what now? So now, which means now your mole of your hydrogen peroxide is going to be given by 0.049, right? This is the mole now of your hydrogen peroxide. And now that you found the mole, I mean, now you can start working backward and see in terms of what is it that you have also. Now, so what is it that you are going to have from this particular reaction is that now already we have this, so you're going to come back in here and say now, since you found out what is going to be the mole, now you're going to say, look, they want you to calculate the mass, right? The mass. And you know that for you to calculate your mass, you're going to say N is equal to your M over your molar mass, or rather your mass over your molar mass. Out again. So, and now what is it that you are then going to do from here is now you are going to come back and say, now from here, what is going to be your molar mass? Your molar mass, you can go in your calculator and calculate. Look, for this, let's try and start with it. Your molar mass of your H2O2, it is going to be given by what? Your molar mass is going to be, look, this is going to be 2 multiplied by 1 plus 16 multiplied by 2. This is 16 multiplied by 2, which means the totality of this is going to be given by what? It is going to be your 34 grams per molar, the molar mass. So then now you come back to the to this and you say now you are looking for your mass of your H2O2, and now you already have your mole. And now remember your mole is this one. So if you are looking for your mass, it's the formula is going to be same as M is equals to what? Your mole multiplied by your molar mass. So this is going to be 34 multiplied by 0,049. Are we together? Then now, and now that we are here, then you're going to plug this in our calculator and see. So our mass, now the mass that we are going to get now for your H2O2, it is going to be what? This is going to be 1,67 grams, right? So now this is how you then calculate your what? Your mass of this. Hopefully, this makes sense to you. Now let's make up some space to now answer the second part of the question now. Let's then look at the second question, your 6.2. Now, look, Patsy, in an experiment, a learner added what? Added your 500 centimeter cubed of your hydrochloric acid with the concentration of 0,36 moles per decimeter cubed to a 1.2 grams of your magnesium in a test tube. She records the change in mass of your magnesium as the reaction proceeds at regular intervals. Now, the balance equation for the reaction is given below. Now, so the balance reaction for this one, it is going to be what? Let's see. Now, so this is going to be what? Now let's understand the question. The question now, firstly, so let's start here. This is your balance reaction. And since this is your balance reaction, now what is it that we can do? Now they say the change in mass of magnesium during the reaction is shown below. So this is the change. So this graph represents the change. So now they say identify the limiting reagent or agent in this reaction. Give a reason for your answer. Now look, now let's start here. What is going to be the limiting reagent for this one? Now if you can check in this one, your limiting reagent is going to be what? Now your limiting for this one, it is going to be your magnesium, right? Your limiting reagent is going to be your magnesium. And now let's see in terms of what is it. So here you are going to have 6.2.1, and we are saying now your limiting reagent is going to be your magnesium. And probably you're asking in terms of why am I saying this is the limiting reagent? Look, now if you can check, now the mass of your magnesium after 3 minutes, right? Or probably at the end of 3 minutes, it was 0, right? So which means now during our reactant, it is the one that was easily or rather it was depleted. Because if you can check here, there is nothing. Now if you can check the mass here, there is nothing that remained after your 3 minutes, which means the magnesium was used up to its totality. within this particular reaction, right? So this is going to be the reason why we are saying then it's the magnesium. So now we are going to say the reason is going to be now the mass of the mass of magnesium after 3 minutes it was 0, right? Or which means, or rather you can say it was used up. It was used up within this particular reaction. So that's why we are therefore saying that is going to be your what? This is going to be then your what? Your limiting reagent, because it's the one that runs out within this particular reaction and it stops or prevents the reaction to continue. Now let's look at now 7.2.2. Now in this one, they say calculate the number of moles of the unreacted hydrochloric acid in the test tube after 3 minutes. Now let's see. Now let's start here in terms of what is it that we are given here. Now if you can check your hydrochloric acid. Now look, for hydrochloric acid, what is it that we are already given in here? And now for hydrochloric acid, you are given, yes, you are given what we regard as your volume. And what else are you then given? You are given also the concentration, right? You are given also the concentration. And the question wants you to calculate the one that did not react. So what is it that you can start with here? Now, because you already given the concentration and look, this is your volume and this is your concentration, right? So you can start now by using this formula. Now, C is equals to your N over V, right? For what? And what are we then calculating for this? We can then calculate what is going to be the mole of our hydrochloric acid. So we're going to say, look, our moles of our hydrochloric acid is going to be given by what? Now, what is the volume? Remember, volume, we always say this is going to be 500 divided by 1,000, which is going to be 0.5 decimeter cube. Remember, because we are moving from centimeter to what? To decimeters. Then now this one is covered. So you come in here now, you say this is going to be 0.5 multiplied by the concentration you are already given that this is going to be 0.36 moles per decimeter cubed, right? And when you are multiplying this two, then the mole of your HCl that you're going to get, it is going to be what? It is going to be your 0.18. It is going to be 0.18 mole, right? Now this is going to be your mole of this one. This is going to be your mole of your HCl. And then now after that, now that we have the mole, look, now that we have the mole, now what is it that we can do? Now we can take the mole in here. And now we want to calculate, because remember, this is the mole of what? This is the mole of the reacted. This is the mole of the reacted, right? Or rather the one that is used. So you can calculate in terms of, if this is the mole of what is used, you can come back and use the formula N is equals to N over your molar mass to calculate now what is going to be the mass or the unused mass, right? And see in terms of what is it that we are going to get. But now we are going to say, now, is there a need for us to do that? No, let's start here. Now, let's start by calculating now what is going to be your molar. What is going to be your mole now of your magnesium? Now, and for us to calculate your mole of your magnesium, this is the formula that we are going to use. Now, if we are calculating our mole of our magnesium now, it's because now we want to find what is going to be your mole of the reacted for our hydrochloric acid. So we already have the used one. Now we want to find out what is the one that we had, right? Now, or rather the one that is left. So we are going to say, no, the mole. Now, if you can calculate what is going to be now your mole of your Mg, which is your magnesium, it is going to be equal to, what is the molar mass? What is the mass there? It was 1,2 over, what is the molar mass of your magnesium? It is going to be equal to 12, or rather 24. Why am I making a mistake there? It's going to be 24, which means now your mole of your magnesium, it is going to be given by what? It is going to be given by 0.05 what? Mole. And now after that, what is it now that we are then going to do? Now we are going to say now this is going to be the one also that is reacted, right? This is the mole that of your what? Of this thing of your magnesium that is reacted. So now if you can then now check the ratio. So if you can check the ratio now here, we are going to say, look, if we can now take your magnesium and your what? Your HCl and say, what was the ratio here? The ratio, it is 1:2 because that's what we are given. The ratio is 1:2. And we say now, what is therefore going to be your mole of your HCl used now? What is going to be your mole here of this one that reacted? Then now the mole that you are going to find in here, you are going to have, now look, what is the our magnesium? So our magnesium, firstly, it was the ratio is 1:2. So therefore, the mole that you are going to get here, it is going to be 0.1 mole, right? This is going to be 0.1 mole of your HCl. And then now that we've calculated in terms of what is going to be the one that also reacted, right? The mole of this that reacted. What is it then that we can do now? We're going to say now, look, what is going to be the moles left in your test tube? Now, the moles left in your test tube. Now, remember, this one is the one that is used, not necessarily reacted, but is the one that is used in this reaction. And this is the only mole that reacted, right? This is the one that was used. Let's fix this one so that you don't, this is the one that was what? This is the one that was used for this entire reaction, the moles that were used for this entire reaction. And this is the one that only was used in this particular reaction. So we want to find out what is the one that is going to be remaining, right? So now, so we are going to say, look, now our HCl left, now, it is going to be given by what? It is going to be your 0.18. Now subtract, what is the mole that was used? It was 0.1. And now, therefore, if you then continue, you are then going to find an answer, and then your answer for this one, it's going to be 0.08 mole, right? So then this is going to be the mole that is left within this particular reaction. Altogether, or the one that did not react, or the unreacted, right? The unreacted mole. So basically now, this is how we are going to deal with these things. And please don't forget, the mole that we are calculating here, firstly, here, is the one that was used in the reaction, and the one that was used in the totality of reaction, this is the one that reacted. That's why we used a ratio, because the ratio gives us the balanced reacted ratio. And after that, now we going to calculate everything like this. So now hopefully this will make sense to you.